So the topic of my talk would be so-called T star equation of Chicotti and Waffa in the context of n equals 2 supersymmetric quantum mechanics. It is related to the theory of primitive form by Yoji Saito, and it is a part of mirror symmetry construction that we will study later. However, I will work today purely on quantum mechanical grounds. So last time we studied n equals 2 supersymmetric quantum mechanics. It was based on chiral and anti-chiral multiplets. Like in n equals 1 supersymmetric quantum mechanics, one may see that operators Q plus, that operator Q plus could be written as Dalbo plus dw, and Q minus was d plus d bar w bar. So I don't want to repeat what I have done for n equals 1 supersymmetric quantum mechanics. It is just similar. All considerations are similar. What is interesting about Q plus? The formation of Q plus correspond to the formations of W and R. And here it's an interesting phenomena happens. Q minus exact. So delta Q plus is actually Q minus commutator of delta W. And this together with harmonic theory gives an interesting mathematical structure. Let me give you the plan of my talk. I will describe two connections on the space of extended cohomology, and I will compare them. As a result, I will get interesting quadratic equations. So let me tell you what would be this extended homology. Let me introduce a spectral parameter that I will call Z. So this parameter has different names in the literature. Someone call it H, that I do not like. Someone call it d over dt 0 minus 1. But I will use Z. So I would like to study QZ, that is Q plus Z Q minus. And where this QZ would act, and I will consider different spaces. I will consider space H, that is, probably I'll call it V. That is differential forms on, so I will consider simple case on Cn. It could be not Cn, but I may even call it X. Let me consider general case times polynomials in Z. And there will be another space, V hat. And here I'll consider formal power series in Z and Z minus 1. Okay? So Z is acting just by multiplication in these spaces. I will also consider WT. That would be W plus TK phi K. So W is a holomorphic function on X. So X is non-compact. Phi K's are also holomorphic functions. Tk are parameters. Example, X is C, non-compact. I would even put it this way. I will consider two examples. So let this be example 1. X is C, that is non-compact. W is X to the power, okay, this is a manifold. X to the power n, where X is a holomorphic coordinate on big X. So what can we say about phi k? X to the power k. And this example is called singularity theory. And it has many generalizations. Example number 2, X is C star. That is C without point 0. W is X plus 1 over X. This example called mirror symmetry example. So what I want from W? To go to infinity when X goes along non-compact direction. To get discrete spectrum of the Hamiltonian. That is minus Laplacian plus dw over dx modulo square plus less relevant terms to have harmonic theory. Okay, so my goal would be to study cohomology of QZ over the base, and the base would be C, and here I would like to put formal power series in T1, Tn. It is called formal disk. So it is a bundle. So I should say H of Z where, sorry, I would like to study H of Z in the space we had. It is a bundle and it has two connections. One connection is very easy and it does not involve harmonic theory. For some reason, it is called Gauss-Manin connection. Idea is the following. QZ is Q plus Z Q minus. If Q plus goes to Q plus Q minus phi, then it may be compensated by transformation omega. It is a simple computation.
I'm sorry, what is omega? Is it the two form on our space?
Where omega is a representative of QZ cohomology. So let us assume that QZ omega equals to 0. Now I'm changing QZ to QZ plus Q minus phi. And then let us try to solve QZ plus Q minus phi applied to omega plus delta omega equals to 0. So how to solve it? I need to solve equation Q minus phi applied to omega plus QZ delta omega equals to 0.
So we consider phi to be like small.
Yes, we consider phi to be small. So it's better to introduce small parameter epsilon, and then we put epsilon also here.
If we use a parameter epsilon, then perhaps we can even look at odd phi's as examples of deformations, right?
Yes, but in principle, yes. But in the example studied here, phi's would be even. So in this, so we are changing W. So we are changing W, that is even, by even phi's. But in principle, you are right. Here W is even and phi's are also even. So we need to find this delta W. So idea is that we can choose delta W. So in this equation, so this is Q plus Z Q minus applied to the delta W. And we can choose and we can solve this equation quite easily by choosing delta W to be 1 over Z phi W. In other terms, Q plus Q minus epsilon phi plus Z Q minus, I can consider the conjugation of it with the help of 1 over Z epsilon phi. And I'll get the correct sign later. So 1 over Z would produce exactly this term. And of course, so this is Q plus Z Q minus. So this deformation can be rotated away by conjugation with e to the 1 over z epsilon phi. And 1 over z standing here cancels z standing here. Here I assumed that q plus phi equals to 0. So here I make a pause, so you may see that such deformation may be undone.
Uh, we're not keeping track of the signs, right? Because I don't think that this is correct. I tried acting with ZQ minus on this exponent. Yeah,
Maybe like this.
I think this is closer to the truth.
So here you just put q minus inside and you get this q minus epsilon term, yes. So in this way, we have omega Gauss-Manin. So it's the horizontal section of the Gauss-Manin connection. With the formula on representatives, delta Gauss-Manin of omega And this is connection number 1. However, there is also another connection on QZ cohomology related to Hodge theory. Idea of this connection. While Q plus is changing, Q minus is not changing. And harmonic forms of Hamiltonian identify cohomology of Q plus with cohomology of Q minus. So there is a connection that is constant on cohomologies of H of Q minus upon this identification. So here I show you the big picture, that there is a harmonic theory here. Question: how to write the formation of omega due to this connection? Answer is simple. Since class in HQ minus is not changing, then delta Hodge of omega should be Q minus exact. So I'm looking how to solve the following problem. And also I want delta Hodge of omega to be Q minus of something. So I can even rewrite it as Q minus applied to phi omega, since I assume that Q minus of omega equals to 0. Let me present a solution to this problem. Let me try to take H homotopy to Q plus. What does it mean? It means that Q plus H anticommutator is 1 minus projector on harmonic form. So I will try the following formula. So let me check if it works. Okay, I'll even put brackets. Now here I have Q minus, Q plus, H phi omega. Now this gives me Q minus.
There should probably be a minus sign. I think they anti-commute, no?
Yes, yes. Yes, so I'm sloppy with the minus sign, yes.
No, I mean, when you exchange the order of Q plus and Q
Yes,
minus.
yes, I am sloppy with minus signs. So So I have minus Q here, Q plus here. Then I replace Q plus H. Then I have here Q plus H. And then I have here the following. Minus Q minus. Here I have anti-commutator. That is 1 minus projection on harmonic forms. And I also have term, okay, plus or minus, it doesn't matter.
It's plus.
HQ plus phi of omega. But this is 0. Now what I have here?
Because phi and omega are both Q plus
Both
closed?
are, yes, because it is harmonic connection. I'm looking how harmonic, I'm looking how harmonic class is changing. So this is 0. Now what happens here? This goes away because Q minus projector on harmonic forms is also 0. So altogether I have this term. And this is the wanted term. That is what I wanted. And this is what I wanted, up to sign. So if I put minus here, signs would go correct. Now, this is a second integrable connection. By integrable, I mean it has no curvature. It has no curvature since it has a global definition given above. Here I wrote it in words. Then I may extend delta Hodge to the full space we had just by tensoring by these objects. Please note that in the definition of Hodge connection, I was not using Z at all, while the Z was crucial in construction of the Gauss-Manning connection. So here you may see that in construction of the Gauss-Manning connection, Z was absolutely crucial. In construction of the Hodge connection, Hodge property was crucial. And then it is instructive, I will write it. If we have one integrable connection, we just trivialize the bundle. No new local information. However, if we have two integrable connections, we may trivialize bundle by first connection and write the second connection as a one form. Difference of two connections is a one form in the endomorphism of the trivialized vector space. So our goal is to write plus some interesting one form A with equations. So suppose we trivialize one of these connections. Suppose we trivialize Gauss-Manning, or maybe it's better to say that we trivialize strategy. Suppose we trivialize Hodge, and we would get from this interesting equations. Since Gauss-Manning would be integrable, it is a strategy. So we need to compare them. So let me tell you how to compare them. I will do it in two steps. Easy case. Suppose that phi omega is 0 in 2 plus cohomology. Then I want to show that in this case, Gauss-Manning and Hodge coincide, which is a statement that I'm going to make. Really, in this case, consider QZ applied to 1 over Z H phi omega. What it is? It is 1 over Z Q plus H phi omega plus, and I need to take a second term, Z 1 over Z Q minus H phi omega. These terms cancel, and here I have 1 over Z phi omega. So up to a sign, so here is a minus sign. So up to a sign that I always miss, these two connections are the same. However, these two connections are different if phi omega is non-zero in Q plus cohomology. In such case, Q plus of H phi of omega is actually projection. One over z phi of omega minus, and here we have an important thing, minus 1 over z, and here we have projection on harmonic forms phi of omega. And this is the crucial difference. And that is interesting. Let us write what happens in coordinates. So we have phi k, tk. Let us introduce the following operator, ci, action of phi I on Q plus cohomology. Then from our consideration, we get the difference between Gauss-Manin and Hodge is 1 over z ci dti. And now I will apply this idea to get such equation. However, equation would be very interesting. It will be an equation with spectral parameter. By trivializing Hodge connection, I will say that Gauss-Manin connection takes the form, and then Gauss-Manin connection squares to 0. From this we find equations. So what is this d? dti, d over dti. From this we will get interesting equations. ci, cj commute. It is a coefficient in front of 1 over z squared. We also have equation djci. Okay, I can even write it like this. This is coefficient in front of 1 over z. 1 and 2 are quite non-trivial equations. We may solve 2 by writing for some matrix valued function tau. Then 1 looks very non-trivial. Written in this form may be called commutativity equation. Interestingly enough, not such equations. Solutions to C equation may be classified by means of integrable equations theory. Let me make more comments on these equations. Interesting example of such equations. It's example 1, where W is x to the power n plus pk x to the power k. How to do Hodge theory? It turns out that harmonic theory may be replaced by theory of holomorphic germs of harmonic forms at 0. So omega harmonic is a complicated one form containing, so omega harmonic depends on x bar, dx bar. In particular, for n equals 2, it is an oscillator, and omega harmonic has the following form. However, harmonic germ, sorry, holomorphic germ. Holomorphic germ means that to take x bar to 0, keeping x fixed is just dx. And the theory may be played on holomorphic germ. In particular, for W germs, holomorphic germ of harmonic form are dx, x dx, xn minus 2 dx. Interestingly enough, not harmonic, sorry, Hodge connection is, and here I write germ. You take phi, you take omega, then you subtract. So what do I mean here? You consider phi omega and you write it as sum of the terms k from 0 to n minus 2 x k dx plus dw times something. And this is phi omega harmonic. So difference between phi and omega. So okay, I assume germ. So difference between phi omega and phi omega harmonic, this piece. So you take this star, so when you divide by dw, you get this star, you apply d, and that's how germ is evolving. And it is possible to write the global formula. But before I write the global formula, I want to say that this piece is just the difference between Gauss-Malin and Hodge. Omega harmonic equals dwk over n plus, where wk over n is what? It is a series x to the k plus something, I don't know, c k minus 1 x to the k minus 1 plus c0 plus c minus 1 x minus 1 plus etc. So wk over n plus means that we are taking only this part. And this is how harmonic germs look like. And related integrable system is known as a dispersionless limit of k reduced, sorry, of n reduced kp equation. So that's what I wanted to tell you in one lecture about two connections and related integrable systems. So the story of two connections. Okay.